Let's go back to PbI2 a little bit. PbI2 solid going to Pb2 plus 2i minus. That's the Ksp expression here. So let's find the Ksp value if the solubility is 0.00130 moles per liter. Now I want to step back for a second and just remind everybody, solubility is a threshold amount, and that's a moles per liter, and that says how many moles of PbI2 can dissolve per liter of water. If you're under that amount, you don't see a solid. But if you go even just a tiny bit above that amount, that's when you'll start to see the yellow PbI2 crash out of solution or form a precipitate. So what we're going to do in this problem is convert the solubility, how many moles of the solid dissolve per liter up until seeing a solid, we're going to turn that into a Ksp, and it's not too bad. Solubility, again, refers to how many moles of a solid dissolve per liter. And when you go above that number, you'll see a solid form. If you're under that number, you won't see a solid form. They should be all able to dissolve in that amount of water. Solubility is literally the moles of PbI2 that can dissolve per liter of water. And notice how PbI2 and lead-2 plus 1-to-1 ratio. So if the solubility of PbI2 is that 0.00130 moles per liter, and you get 1 mole of lead-2 plus for every 1 mole PbI2, the solubility of the lead-2 plus is going to be the same as the solubility. It's 1.30 times 10 to the minus 3. So solubility and the amount of lead that's dissolved are the same number here, and that can be a little strange. The iodide is, of course, part of it too. Iodide will be twice the lead. Stoichiometry again, 2 I's for every 1 Pb2 plus. 2 iodides dissolve for every mole of PbI2 in the solubility. So iodide here is going to be 2.60 times 10 to the minus 3. Notice here again how stoichiometry of the balanced reaction is so important. 2I minus per 1 lead, we multiply the lead by 2 to get the iodide, no problem. There's a couple ways you can go from here. We want to find the Ksp, okay? And one way you could do it was you could just plug the lead value in, this number, and multiply it by the iodide squared. Remember, this is an equilibrium expression, products divided by reactants. No reactants, because our only reactant is a solid, but we do multiply or square the iodide, multiply it by a factor of 2 because of the stoichiometry of 2. So again, you could take 1.30 times 10 to the minus 3, the lead 2 plus, and multiply it by 2.60 times 10 to the minus 3 squared, and that would be fantastic. But notice this version as well. You could also take the iodide, and iodide was equal to 2 times the lead. So there's a reason why I'm doing this. I'll talk about in a little bit. So 2 times the lead, quantity squared, because we still have to deal with that thing. 2 squared is 4. Lead 2 plus to the second power is lead squared, but we're multiplying it by this lead 2 plus. 4 times the lead 2 plus to the third power would be one way to solve for this Ksp, and I'll talk about why I'm doing it this way here in just a second. To figure out Ksp, there's 2 ways you could do it. You could literally take the lead and multiply it by the iodide squared, and that's fantastic. But if you go through a little math, you'll also see that Ksp equals 4 times the lead ion to the third power. And there's a use for that here. I'll show you in a little bit. Anyway, whichever way you do it, you can absolutely get the right value. Lead 2 plus, remember, was equal to the solubility. So you can rewrite 4 times lead 2 plus to the third power as 4 times the solubility to the third power. I'm going to do my problem this way. I'm going to take that solubility and cube it first and then multiply by 4, Ksp 8.79 times 10 to the minus 9th. Now, again, you would have gotten the same value if you would have taken 0.00130, the lead, and multiplied it by 0.00260, the iodide squared. It doesn't matter which way you do it, but this 4 times the solubility to the third power equals Ksp will be helpful to us here in a little bit. But this is one way that you can calculate then Ksp from solubility. So in this problem, solubility was related to PbI2, and if you think about solubility as x, Ksp equals 4 times x to the third power. The solubility to the third power times 4 equals Ksp. And you're probably like, what are you doing, Russell? Have you been out smoking or something? And no, just say no, kids. There's a reason for it. A lot of times, a scientist will have Ksp and they want solubility. Or, like in this problem, you'll have solubility and you want Ksp. And you can actually go through stoichiometry and figure out the different pieces. But if you know the relationship between Ksp and solubility x, it does make your life a little bit easier, which I know is kind of strange sounding. This page shows the different relationships between solubility x and Ksp. Now, in the first one up here, there was one cation and one anion. So for things like sodium chloride, Ksp would be sodium ions times chloride ions. And because solubility is how much of each of those are created, it would be like x times x or x squared. So if you had a Ksp for NaCl and you wanted to find the solubility, you could take the square root of Ksp and that would equal solubility. And that also works for things like strontium oxide, which are one cation to one anion. Potassium chlorate would be 1K plus and 1 ClO3, one cation to one anion. All of those work really well. Now, the next two are very similar. If you have one cation and two anions, like PbI2, or if you have two cations and one anion, then Ksp equals 4 times x to the third power. So in the last example we were looking at, I think it was lead to iodide, PbI2, if we had the solubility to the third power times 4, that's going to be a great way to find Ksp. And again, that works for any time you have two cations and one anion, or one cation and two anions. Those three examples are going to be very common. However, you can figure these kind of things out for other systems too. If you have a 3-to-1 ratio of cations to anions, Ksp equals 27x to the fourth. And if you have two cations and three anions, or three anions and two cations, Ksp equals 108 times x to the fifth power. And believe it or not, I have used all of these at different times to calculate solubilities, Ksp, and stuff like that. And it's a little bit easier if you can do the solubility x to Ksp conversion. Let's look at some examples. So let's say we wanted to find the solubility of copper 2 phosphate if Ksp equals 1.4 times 10 to the minus 37th. So what we would have to do in a problem like this is first of all find that ratio of cations to anions. Well, copper 2 means copper 2 plus. And phosphate, a polyatomic ion, PO4 negative 3. So when they come together to make a neutral compound, you can use crossover or whatever you want, Cu3 PO42, that would be the formula for copper 2 phosphate. We have 3 cations and 2 anions. And if I'm correct here, Ksp equals 105 times x to the fifth. Let's see if I was right. 108 times x to the fifth. Sorry about that. So because there are 3 cations, 3 copper 2 pluses, and 2 anions, 2 phosphates, this is a 5 total anion ratio, 3 cations, 2 anions. And the relationship, if you look back to that slide, between 3-to-2 and a Ksp, it's 108 times x to the fifth equals Ksp. So in this problem, we have the Ksp and we want to find x, the solubility. So you can take the 1.4 times 10 to the minus 37th, first divide by 108, and that'll give you solubility to the fifth power. And then you need to take the fifth root, which is like raising it to the 1/5 power. In your calculator, this can get kind of messy, but it's actually pretty easy to plug and chug once you see it. Here's the Ksp. We're dividing it first by 108, And to get rid of that x to the fifth, you raise it to the 1/5 power. Just like 2 squared is 4, and the square root of 4 is 2, and the square root is like 1/2. So x to the fifth, the opposite of that, if you will, would be 1/5, all right? That's where that comes from. Anyway, solubility, 1.7 times 10 to the minus 8th moles per liter. So copper 2 phosphate will not form a solid unless those ions are pretty small, like that number right there. In reality, the copper would be 3 times that number, and the phosphate would be 2 times that number. But don't even worry about that right now. This is a cool way to go from an equilibrium constant back to solubility, or from solubility to Ksp. Here's another problem. What is the Ksp for magnesium carbonate if the solubility is 2.6 times 10 to the minus 3? Now, magnesium is a positive 2 alkaline earth metal, carbonate, a polyatomic ion, CO3 minus 2. This is a 1-to-1 ratio, 1 magnesium for every 1 carbonate. So this solubility is going to be related to Ksp by Ksp equals x squared, because we only have 1 cation and 1 anion. So solubility squared in this case is going to give you Ksp. If you take that 2.6 times 10 to the minus 3 and square it, that's going to give you Ksp 6.8 times 10 to the minus 6. Now, at this point, you might be thinking, yeah, whatever. All right. And I totally understand. You also might be thinking, hey, why don't they just talk about solubility and forget the equilibrium constant? And that's a really good question. Equilibrium constants, KSPs, have a lot more uses than just converting back and forth to solubility. So one of the uses of KSP is to calculate the solubility, i.e., if you put the solid in water, how much of it will dissolve, or how much do you have to stay under in order for it to remain dissolved. So that's a cool use of Ksp, but we're going to see there's other uses of Ksp besides just solubility, so hang tight. The solubility of barium sulfate, 1.05 times 10 to the minus 5. What's the Ksp? Well, barium sulfate, if you remember from before, it's a barium 2 plus and a sulfate negative 2. They come together 1-to-1, BaSO4. So BaSO4, 1-to-1 cation to anion, means Ksp here would equal barium 2 plus times sulfate, or if we're talking about solubility, Ksp equals solubility squared, x times x. And we have there the solubility number, so take that number and square it or multiply it by itself. The answer, 1.10 times 10 to the minus 10. So again, a very small Ksp for a very insoluble compound. Here's an example with that weird mercury 2 ion. This is Hg2Cl2, which is very insoluble. It's breaking down to the mercury 2 plus ion and 2 chlorides. Now Ksp for this reaction, 1.1 times 10 to the minus 18th. And again, that's going to equal the product of the ions, nothing on the bottom because no solids or liquids. Ksp equals mercury 2 plus times the chloride ion squared. Now, let's say that we had a solution of this mercury 2 plus hanging around, and it was 0.010 moles per liter. And mercury is not exactly the best metal to be having around, and if you're not using it, you should probably dispose of it properly. And one way to dispose of things properly is to make a solid. If you make a precipitate, then you can filter out the solid, and shipping solid waste is a lot easier and a lot safer, honestly, than shipping waste with a solution, like the 0.010 molar thing is. So let's say we're going to be good people here, and we're going to try and precipitate out that mercury 2 plus ion as Hg2Cl2. Well, if the mercury 2 plus is 0.010, and we know that Ksp, the 10 to the minus 18th number, equals the mercury times the chloride ion squared, I wonder what chloride ion concentration, moles per liter, is required to begin precipitation of this Hg2Cl2 salt. And that's a really, really good question. This problem, when you see it, is a pretty easy plug and chug. You put the right pieces in the right equation and out the answer will come. But at first it can be kind of weird to see. Questions like this also show the utility of Ksp. So instead of just finding solubility, i.e. when solids will appear, now we have an unusual amount of mercury and we want to see how much chloride it's going to take to make the precipitate crash out of solution, become a solid. The question really is even better, though, than I said it. Really the question is, what's the maximum chloride that can be in solution with that 0.010 molar without forming the mercury 2,2+, i.e. what is the solubility when you have 0.010 molar Hg2+ ions? And that's a really, really good question. And we can use that Ksp, this thing up here, to plug it in. And honestly, it's pretty chill. This number goes right there. We've got Ksp. We're going to solve for chloride ion. It's going to be squared, so you have to take the square root, etc., etc. So let's do that. Ksp 1.1 times 10 to the minus 18th, the number you can look up, equals mercury ion times chloride ion squared. Mercury ion was the 0.010. Now, Ksp is the product of the maximum ion concentrations. When you go over these thresholds, that's when a solid begins to appear, and when you're under the thresholds, then you don't have a solid. So when we figure out what this number is, all right, we're going to get a number. And if you go just a little bit above that number, that's when you're going to see a solid form. It's when it exceeds the Ksp, the maximum ion concentrations. And in this case, we're going to find that threshold for chloride and see when the solid will start to happen. Going back to my plug and chug equation, the Ksp 1.1 times 10 to the minus 18th equals 0.010 times chloride ion squared. So we want to solve for chloride. That's literally all we do. So chloride squared is going to equal Ksp divided by the mercury, 0.010. To get rid of the squared, we'll take the square root of both sides. So Ksp 1.1 times 10 to the minus 18th divided by 0.010, and square root of all of that, 1.0 times 10 to the minus 8th moles per liter. And this number is actually pretty helpful to chemists, because once you go past that amount of chloride, you're going to start seeing insoluble Hg2Cl2. If you go to 1.01 times 10 to the minus 8th moles per liter chloride, you're going to see a solid. However, if you're only at 0.9 times 10 to the minus 8th molar, a little less than that, no solid is going to form. So that's the utility of this kind of thing. It doesn't take a lot of chloride to make this stuff crash out, to make it precipitate. It's easy to have 10 to the minus 8th. Goodness, in the lab we'll use 0.1, 0.01, 0.001 maybe solutions. 10 to the minus 8th is very, very small. Let's say that we know that it's the 10 to the minus 8th moles per liter needed to make the precipitate crash out. Let's add a lot of chloride. Chloride is cheap. It's in sodium chloride. Even hydrochloric acid isn't too expensive. So let's really push the chloride up. If you push the chloride to 1 moles per liter, when the mercury was initially 0.010 moles per liter, well, by Le Chatelier's principle, if you add a lot of product here, chloride, it should make the reaction move to the left. So the mercury, which was 0.010, should be a lot less as we pump the chloride up to 1 mole per liter. And we can use this technique to calculate the new value of the mercury ion at this point. So Ksp equals the mercury ion times the chloride squared. But in this example, we're solving for the new value of mercury. And mercury at this point will be Ksp divided by the chloride squared, which is just 1 squared. So lo and behold, mercury 1.1 times 10 to the minus 18th moles per liter. And when you think about these numbers a little bit, we took a solution which was 0.010 moles per liter, and we dropped it. We kicked it way down. So now the mercury ion concentration, 1.1 times 10 to the minus 18th. And so if we were trying to get rid of the mercury, that's pretty good. That's a reduction of concentration by 10 to the 16th, 10 to the minus 18th versus 10 to the minus 2 in the initial thing. That's pretty powerful. That's pretty cool. But it's also worth pointing out that we have not lowered the mercury to 0 moles per liter. All right? It's a very, very small number. 10 to the minus 18th is very, very small, but it's not 0. And you as a scientist and as a person and as a member of society need to figure out, is a 10 to the minus 18th moles per liter mercury concentration safe? Is that a good number to drop it to? Most people, I think, would say yes, that's pretty safe, but some people maybe don't. And this is something you need to think about as a person. I'm not going to tell you what's right or wrong. I do want to point out, though, that you can lower these concentrations a lot, orders of magnitude less than they were. But you as a person and as a member of society and all that kind of jazz, you need to think about if that's a truly safe level or if you need to add more in order to make the concentration go even lower. And finally, I don't think it's really possible in most situations to get that value down to 0, to literally have 0 moles per liter mercury to, unless you have something like sodium and water, which is very, very product favorite. It's very difficult to get these down. You can get them very, very low, but they won't go to 0. And that's kind of an interesting thing. That's an advantage and a disadvantage, arguably, of equilibrium. Here's a question. What concentration of carbonate is required to begin the precipitation of insoluble strontium carbonate from a solution which has 0.050 molar strontium 2 plus? And there's the Ksp for strontium carbonate, 5.6 times 10 to the minus 10. Okay, most of the time, all right, you're going to solve for one of the missing pieces in the Ksp expression. And for this problem, you would write SrCO3 solid in equilibrium with the ions, strontium 2 plus aqueous, and carbonate aqueous. And again, I can't draw on this thing worth anything, so I apologize. But Ksp would equal the strontium times the carbonate. And you can see here that you have a concentration of the strontium and you have a Ksp for this thing. So the only thing you don't have then is the carbonate, the concentration of the carbonate. That's what you want to solve for here. So you can take Ksp and divide it by 0.050, and whatever that is, that's going to be the answer. So when you do that, it comes out to be 1.1 times 10 to the minus 8th. That's the level of carbonate required to precipitate strontium carbonate from a solution. And again, it's pretty small. Strontium carbonate really wants to form. That's a very small K. Good to go.